Hey, welcome. This audio is to help you revise MCS-213 for your IGNU MCA exam. We're going to dive deep into the important topics one by one in order, and don't worry, I'll highlight any areas that have frequently appeared in previous exams so you know exactly where to sharpen your focus.
That's right. Think of this deep dive as, well, your essential shortcut to being truly well-informed for your exam. We'll simplify complex software engineering concepts, helping you grasp not just what they are, but why they matter, in the real world, making your revision systematic and genuinely easy to understand.
Okay, let's unpack this with the evolution of software development and what software engineering is all about, starting with Unit 1. So cast your mind back to the early 1980s. Software development was a bit like the Wild West. Not a lot of rigid rules, mostly individual heroics. We saw the rise of languages like Pascal and COBOL, making programming somewhat easier. And, basic ideas like structural design and quality assurance emerged. But the business side, like estimating costs and timelines, was largely guesswork.
What's truly fascinating here is why this chaos had to change. Imagine building a bridge where the engineers just, felt it would hold up.
Yeah.
Or a medical device that constantly crashed. Historically, software projects often wildly missed their costs and schedule targets, and the final products were just riddled with defects. Software development couldn't just remain an art.
Right.
The critical shift to software engineering was about bringing scientific discipline to this process, making it predictable, reliable, and measurable. This meant we needed systematic approaches for costs, duration, risks, defects, demanding measurable qualities for both the software itself and the process used to build it.
So once we understood why software development needed to become engineering, the next logical step was figuring out how to actually build it systematically. And that's where these blueprints, our software development models from Unit 1, Section 1.3.2 come in. Think of them as like different playbooks for building software.
Precisely, each with its own strengths and weaknesses. Let's start with the simplest, the build and fix model. It's exactly what it sounds like. You code, and then you fix.
And fix, and fix.
And fix until the client says it's good enough. It's incredibly basic, often leading to endless cycles. Very inefficient.
Yeah, sounds frustrating. From there, most teams move to something more structured, right? The waterfall model. This is the simplest, oldest, probably most widely used process model, often considered the first true engineering approach.
It is. It's strictly sequential. You finish requirements, then design, then coding, testing, and finally maintenance, step by step. Sounds intuitive.
It does.
And this is an important topic for your exam. The waterfall model has definitely been asked about in previous exams. While it was a breakthrough, its biggest hurdle is its inflexibility. You don't get a working version until very late.
Right, so you can't show anything early.
Exactly. Problems might not be detected until much later, becoming incredibly costly to fix. There are slight modifications with feedback loops, but fundamentally it lacks early risk assessment.
Okay, so next we have the iterative enhancement model. This is where you deliver the product release by release, gradually adding features. Sounds more flexible.
It is. It's useful with limited resources or maybe tight deadlines, especially for in-house development where the user gets something functional early on to work with.
But what's the catch?
Well, the main challenge with iterative models can be that the iterations sometimes feel endless.
Like it's never really finished?
Kind of, yeah, delaying the final product. And estimating costs across these evolving releases can become quite complex,
Okay, then there's the prototyping model. Here you initially build a stripped-down working model, a prototype with limited features and maybe lower reliability at first.
This model is really clever because it tackles one of Waterfall's biggest weaknesses head-on. It gets early feedback from the customer.
So the user gets to see something tangible early.
Precisely. They interact with a rough version, helping you nail down user requirements more deeply and providing crucial input for the actual product. It even allows for some initial risk consideration. But you have to be cautious.
How so?
Sometimes people expect too much from these early prototypes, and if requirements are loosely defined or maybe technology shifts midway, you might end up having to re-engineer the whole thing later.
Right, got it. Finally, we arrive at the spiral model. This one sounds more complex.
It's quite comprehensive, yeah. It cleverly combines the strengths of various other models, making it particularly good for handling uncertainties and, importantly, managing risk throughout the entire project lifecycle.
Okay. Now, once you've picked your development model, how do companies actually measure how well they're doing? That brings us to software engineering process maturity and the SEI CMM. That's the Software Engineering Institute Capability Maturity Model from Unit 1, Section 1.4. It evaluates how mature and effective a software company's processes are.
Exactly. The SEI CMM defines 5 distinct maturity levels. Level 1, initial, is where most organizations begin. Development is ad hoc. Success often depends purely on individual heroism, the gurus.
Right, the superstar coder.
And quality prediction is difficult. And this level is important for your exam, as SEI assessments consistently highlight that most organizations are still at level 1.
Okay, so after initial, you have level 2, repeatable. Here, organizations start establishing basic project management policies and learn from past successes, reusing effective practices.
Correct. Then level 3 is defined. Here, standard software development and maintenance processes are documented and integrated organization-wide. It's about having a clear, consistent playbook that everyone follows.
Moving higher, level 4 is quantitatively managed. This sounds serious.
It is.
Yeah.
This is where measurable standards are applied to the software process itself, and product quality is rigorously understood and managed using data. It's all about putting numbers to quality, making it objective.
And the top level.
That's level 5, optimizing. Here, organizations focus on continuous process improvement. They use quantitative feedback, proactively prevent errors, and adapt to new technologies based on solid cost-benefit analysis. Each level is tied to key process areas, or KPAs, which are indicators of performance, like defect prevention or quantitative process management.
All right, let's get into the step-by-step with the phases of the software development lifecycle, SDLC, from Unit 1, Section 1.5. Remember, software is a product, and building it is a process. These are the generally defined stages that guide that journey.
Absolutely. First up, requirements analysis. This phase defines the what of a system, the objectives the software absolutely must achieve. The key output here is the Software Requirements Specification, or SRS document. Very critical document.
After requirements comes design. This is where you develop the detailed blueprint for the software, much like an architect draws plans before construction starts.
Exactly. Once that blueprint is ready, we move to coding. This is where the design is translated into executable code, and good coding standards are vital here.
Why is that so important?
For readability and, crucially, future maintenance. Think about someone else having to understand your code years later. Standards help immensely.
Makes sense. Then there's software testing. This is about running the software with specific inputs with the sole intention of finding errors. The goal is to deliver truly robust, reliable software.
And it's crucial to differentiate this from debugging. People often mix these up. Testing finds the existence of defects. It tells you that something is wrong.
Right.
Debugging locates and corrects them. It's the fixing part. When testing, you aim to thoroughly cover all parts of the code, even deliberately passing wrong data to push its limits, See how it behaves under stress.
And finally, we round out the cycle with maintenance, ensuring the software continues to function, adapt, and maybe evolve after it's been deployed. Now let's zoom in on principles of software requirements analysis in Unit 2. You mentioned the SRS earlier. This part is often seen as elementary, but paradoxically, it can be the most difficult part of system design.
It really can be, because it's about accurately defining what the system truly needs to do. If you get this wrong, everything built on top of it suffers. It's the foundation.
So the definition matters.
Tremendously. The requirements definition, according to IE standard, specifies the conditions or capabilities a system must meet, derived directly from the user. The overall quality hinges on how well these are defined. Core activities include identifying user needs, preparing that SRS we talked about, and then rigorously validating that SRS for consistency, completeness, and feasibility.
Okay, so how do you actually get these requirements?
Right.
What are some practical requirement gathering techniques?
Well, there are several. You can start by simply observing existing operations and studying documents that's efficient for understanding current systems.
Okay, low effort.
Relatively.
Yeah.
But for new insights, interviews are powerful, those one-on-one interactions to identify needs. They do require skill, though, in asking the right questions, listening.
Right. And for bigger groups?
For larger numbers, a questionnaire can be very effective. It's less effort per person, provides a written record, and gives respondents time to think and give accurate answers. And explaining requirement gathering techniques has been a frequent question in previous exams, so this is definitely one to focus on.
Good tip. Yeah. Once gathered, those requirements need to be documented properly in the Software Requirements Specification, or SRS. You called it the Bible for the project.
It really is. It's the definitive contract, clearly laying out exactly what the software needs to do, how it interacts with the outside world, external interfaces, and any non-negotiable rules like performance or security constraints.
And you mentioned the structure is important for exams.
Yes. Pay close attention here. The
Yeah.
sections of the SRS are a key topic in previous exams. Its typical structure includes an introduction, purpose, scope, an overall description, specific requirements, and then appendices and an index. Within specific requirements, the crucial distinction lies between functional and non-functional requirements. Functional requirements describe what the system is supposed to do, like the system must allow users to log in. Pretty straightforward.
And non-functional.
Non-functional requirements specify how the system performs its function. Things like performance, login response time must be under 2 seconds, or security levels, reliability targets, usability aspects, and differentiating these with clear examples is a commonly asked exam question, so make sure you can explain both.
It sounds like a thorough process, but you hinted it's not without challenges. What are some common problems of requirements engineering?
Oh, there are quite a few. It's genuinely tough to define all requirements perfectly up front. Things change, and project schedules rarely adjust easily for those inevitable modifications.
Right, scope creep.
Exactly. Sometimes there's an over-reliance on case tools, creating maybe false requirements, or tight schedules simply cut down vital analysis time. And a big one, communication gaps. Users and developers often speak different languages, technically speaking, leading to misunderstandings.
Okay, let's talk about modeling and requirements analysis from Unit 2, Section 2.3. Modeling is so important because it helps you visualize the system, right? Takes abstract ideas and makes them more concrete.
Absolutely. It helps everyone analyze functionality by developing a visual representation. One of the most fundamental tools here is data flow diagrams, or DFDs. A DFD is basically a picture showing how data moves through a system.
And you mentioned this comes up in exams.
Yes. The concept of DFDs, sometimes even asking you to draw one for something like a library information system, has appeared in previous exams. Its symbols are simple. Arrows for data flow, circles for processes that transform data, rectangles for external sources or destinations, and open-ended rectangles for data stores, like files or databases. DFDs use a layered approach. You start high level with a context diagram, level 0 showing the whole system as one bubble with just inputs and outputs. Then you drill down into lower, more detailed layers. Key rules include unique names, numbering processes logically, and ensuring every process has at least one input and one output. Keep them clean, not too complex on one diagram.
And to help with that complexity, you use the data dictionary.
That's right. Think of a data dictionary as a catalog or a glossary for all the data elements in your system. It reduces DFD complexity by providing the specific details about the data shown in the DFD.
What kind of details?
It captures info like the attribute name, e.g. employee ID, its type, numeric, text, size, any related data items, valid range of values, and maybe definitions of data structures. For example, it might define payroll as being composed of employee name plus admin number plus address, and so on. And just so you know, the data dictionary itself is sometimes a direct question in previous exams.
Good to know. And then there are entity relationship, or ER diagrams.
Right. ER diagrams are all about modeling the relationships between data objects, which we call entities. Think of entities as the nouns of your system, like student, course, professor.
Okay.
Then you have relationships that show how these entities are associated. For example, a professor teaches a course, a student enrolls in a course, and entities have attributes, which are their properties, like a student has role name, address.
And cardinality.
Ah, yes. Cardinality defines how many instances of one entity relate to instances of another. Is it one-to-one, like one department head per department, one-to-many, one professor teaches many courses, or many-to-many? Many students enroll in many courses. ER diagrams usually show this graphically.
Now let's dive into software design, covered in Unit 3. This is where you develop that blueprint for workable software. You said it's central to software engineering, and crucially, quality is built into the software during this phase.
Precisely. It's not something you just test in later. The primary objective of architectural design is to develop the overall structure and organization of program modules. It defines the high-level components and how they connect, not the nitty-gritty details inside them yet. Think of designing the major sections of a building foundation, floors, roof, before detailing each room's plumbing.
And this leads us naturally to modularity and its importance. Breaking software into modules seems like common sense for organization, but it's more than that, right?
Oh, much more. It's fundamental. Modular design facilitates future maintenance hugely. If you need to change something, hopefully you only need to touch one module. It also allows for parallel development. Different teams can work on different modules concurrently.
Okay. And within modularity, you have cohesion and coupling. Let's start with cohesion.
Right. Cohesion measures how functionally related the elements within a single module are. Think of it as how focused the module is. High cohesion is what you want. It means the module performs exactly one well-defined function, like a specialist doctor. It's good because it usually leads to minimum coupling with other modules.
Which brings us to coupling. What's that?
Coupling is the degree to which different modules interact with or depend on each other. We always strive for low coupling, minimal interaction.
Why is low coupling so desirable?
Because it reduces the ripple effect. If modules are loosely coupled, a change in one module is much less likely to unexpectedly break another one somewhere else. It also makes reusing modules in other projects easier and improves your ability to understand a module in isolation without needing to know about lots of others. And definitely remember this. Coupling and its various types have been asked about in previous exams.
What are some types?
Well, the best type is data coupling, where modules just share necessary data through parameters. Then there's stamp coupling, sharing a data structure, maybe passing more data than needed. Control coupling, one module controls the logic flow of another. And going towards worse options, common coupling, sharing global data risky. And the worst is probably content coupling, where one module directly modifies another's internal data or code. A real no-no. Generally, high cohesion often correlates strongly with low coupling. Aim for that.
We also need to talk about the user's view. Human-computer interface, HCI design. This seems increasingly important.
Absolutely critical today. Good HCI design involves several key guidelines. You need consistency, use the same terms, layouts. Enable expert users with shortcuts. Don't make them click through everything every time. Provide informative feedback so users know what the system is doing.
And error handling.
Crucial. Good error prevention and handling. For instance, let users select from a list rather than typing freeform where possible to avoid typos. And always allow a way out, a cancel button, an undo. Warn users before they perform critical, irreversible actions. Basically, make it easy to use and hard to mess up.
Beyond just usability, there's user experience, UX design. What's the difference?
UX is broader. It's about the overall feeling the user has when interacting with the application. Is it pleasant, intuitive, frustrating, thrilling? It encompasses HCI, but also considers the entire journey. And related to modern design, you also have trends like designing for mobility and using established design patterns for reusable solutions to common problems.
Let's shift focus now to software quality and formal technical reviews in Unit 4.
Yeah.
You mentioned software quality assurance, or SQA, spans the whole process.
Yes, it's an umbrella activity. Software quality itself. Well, it's about conformance to the stated and implied needs of the customer. Good quality software is often defined as being reasonably bug-free, delivered on time and within budget, meeting requirements, and being maintainable. But quality is subjective sometimes.
How so?
An end user might define quality mainly as easy to use and no crashes, while the developer maintaining it might prioritize well-structured, understandable code. Both are valid aspects of quality.
So how do we assure that quality throughout?
That's the role of software quality assurance, SQA. It involves planned, systematic actions to ensure the software conforms to its technical requirements. And importantly, SQA also evaluates the development process itself. It's the process capable of producing quality software. A key activity within SQA is the formal technical review, or FTR.
FTR, and you mentioned reviews come up in exams.
Yes, software reviews, including FTR and its different types, have definitely been asked about in previous exams, so this is important. The core purpose of an FTR is to discover errors early in requirements, design, code, test plans, wherever they might hide. It also verifies that standard procedures are being followed uniformly.
Are there different kinds of reviews?
Broadly, yes. You have informal reviews like quick meetings or just having a colleague desk check your work. And then you have formal reviews like the FTR, which are structured, planned activities with defined roles and outcomes. The FTR process involves carefully reviewing key documents at each major phase: the SRS, the design documents, SDD, even the source code itself, checking for completeness, consistency, traceability, adherence to standards.
What happens after an FTR?
The outcome is a documented meeting decision, maybe accept as is, accept with required changes, or sometimes reject, needs major rework. This is all captured in a review summary report. We should also briefly touch on software reliability here, essentially, the probability of failure-free operation for a specified time. Mean time to failure, MTTF, is a common metric. And finally, organizations often use software quality standards like the SCI CMM we discussed, or ISO 9001, to help establish and maintain consistent, high-quality processes.
Okay, let's talk money and time. Software project management, specifically estimation from Unit 5. It's almost notorious how often software projects go over budget or miss deadlines. Estimation seems critical.
It's a huge challenge and a core responsibility for project managers. The process of software estimation involves using specific techniques and procedures to arrive at realistic figures for project cost, time needed, effort involved, usually in person months, and the overall size of the software.
Why is it so hard? Why the need for specific metrics?
Well, historically, estimates were often way off. Software development is inherently complex, with many unknowns early on. So there's a strong need for project metrics. We need scientific, measurable ways to track progress and predict outcomes, not just rely on gut feelings.
What kind of metrics are used?
They broadly fall into product metrics, measuring characteristics of the software itself, like lines of code, LOC, or function points, and process metrics measuring aspects of the development process, like time spent or effort expended. LOC is simple, but has issues. It varies by language, doesn't reflect complexity well. Function points are often better as they measure size based on user-visible functionality, making them independent of the programming language used.
Okay, so once you have metrics, how do you actually estimate? What are the steps involved in software project estimation?
This is another area to watch out for. The steps involved in software project estimation have been a common question in previous exams. The general flow usually starts with effort estimation. You estimate the total person months needed. Then you move to schedule estimation, translating that effort into a realistic calendar timeline, often using models. Finally, there's cost estimation, which includes not just the cost of the effort, salaries, but also other things like hardware, software tools, travel, training, etc.
And speaking of models, the Kokomo model seems to be a big one in this area.
It absolutely is. The Kokomo model is a very common exam topic. Kokomo stands for Constructive Cost Model, developed by Barry Boehm. It's a widely used model to estimate project effort and cost.
How does it work? Are there different versions?
Yes, it has 3 levels. Basic Kokomo gives a rough estimate based primarily on the estimated lines of code, LOC. Intermediate Kokomo refines this by considering program size and a set of cost drivers factors that influence effort, like required reliability, database size, personnel capability. Detailed Kokomo incorporates all of Intermediate Kokomo, but applies the cost driver's impact to each phase of the development lifecycle separately.
Does it apply to all types of projects?
Kokomo defines 3 classes of software projects it applies to: organic, relatively small projects, small experienced teams, familiar environment; semi-attached, intermediate size and complexity, mixed experience levels, maybe some rigid requirements; and embedded projects developed under tight hardware, software, or operational constraints, often complex. The basic effort equation looks like E size BM, where size is typically KLOC, thousands of lines of code. A and B are constants depending on the project class, and M is a multiplier based on those cost drivers we mentioned.
Okay, moving on to Unit 6. Risk management and project scheduling. A risk, you said, is a potential problem, something that might go wrong.
Exactly. It's uncertain, but it could negatively impact the project cost, schedule, quality. So the first step is identification of software risks, recognizing where things could go wrong. This might stem from improper technical knowledge on the team, lack of communication, changes in the market, hardware resource issues, maybe even actions by competing companies.
Once you've identified them, what next?
You need ongoing monitoring of risks. A common practice is to maintain a risk monitor table or risk register. This tracks things like the risk name, the part of the project it affects, maybe who's responsible, its priority, and its current status. You update it regularly to see if risks are becoming more or less likely, or if new ones appear.
And actually dealing with them. That's risk management.
Yes. Management of risks involves several techniques. And again, risk management techniques have been asked about in previous exams, so definitely understand these. It includes risk anticipation, trying to foresee risks based on past projects or experience. Risk detection involves actively looking for risks, maybe using tools or checklists, and performing risk analysis.
Risk analysis.
That means evaluating the probability of the risk occurring and its potential impact or weight factor. Multiplying these gives you the risk exposure. High risk exposure means high priority tackle that one first. Risks can be categorized too: people risks, management risks, technical risks, customer risks. After detection comes risk control, taking actions to reduce the probability or impact. And if a risk does happen, you need risk recovery plans, how to deal with the consequences.
Beyond risks, project managers obviously need to plan the actual work, formulating a task set for the project.
Right. This involves breaking the project down into manageable tasks. Factors influencing this include the technical expertise available, ensuring customer satisfaction points are met, how modules are connected, dependencies, defining clear milestones, significant achievements, or deliverables for each phase, and ensuring time for validation and verification.
And then you schedule these tasks.
Exactly. Scheduling methods are about prioritizing these tasks and assigning timelines and resources, considering cost, duration, and dependencies. A common technique is the work breakdown structure, WBS, where the project is hierarchically decomposed into smaller and smaller pieces of work, often shown as a tree diagram. Other methods include activity graphs, critical path method, CPM, Gantt charts, and PERT charts. All these elements, scope, milestones, budget, estimates, resources, risks, schedule, people, quality control come together in the software project plan, the master document guiding the entire project.
Let's delve deeper now into software testing in detail. Unit 7. We established testing is about finding errors, distinct from fixing them, debugging.
Absolutely critical distinction. To reiterate, testing finds the existence of defects while debugging locates and corrects them. Now, for selecting test cases, two fundamental strategies are black box testing and white box testing. And you guessed it, the difference between black box and white box testing is a very common exam question.
So black box.
Black box testing derives test cases purely from the functional specifications, the requirements. You treat the software like an opaque box. You know what input goes in and what output should come out, but you don't know or care how it works inside. The big advantage: you can design these tests early, even before the code is written or the design is finalized.
And white box testing, then, is the opposite.
Exactly. White box testing, sometimes called glass box testing, derives test cases based on the internal structure, the design specifications, or the actual code itself. You're looking inside the box, examining the pathways, the logic, the conditions.
Okay. Are there specific techniques within these?
Yes. A key technique, often associated with black box testing, is boundary value analysis. The idea is that errors are much more likely to occur right at the edges or boundaries of input domains. So if a field accepts values from 1 to 100, you'd specifically test values like 0, 1, 100, and 101. You test right on the boundary and just outside it.
Makes sense. Check the edges. What about equivalence partitioning?
This is another black box technique. It involves dividing the input domain into equivalence classes, sets of input values for which the program is expected to behave similarly. For that 199 range example, you'd identify classes like less than 1, invalid, between 1 and 99, valid, and greater than 99, invalid. Then you pick test cases from each class, typically one from the middle and ones at the boundaries. It avoids redundant testing within a class.
And moving towards white box, what's coverage-based testing?
Coverage-based testing aims to ensure that your test cases exercise as much of the program's structure as possible. There are different criteria. Statement coverage aims to execute every single line of code at least once. Path coverage, which is much harder, aims to execute every possible logical path through the program's control flow. Analyzing the program's control flow graph, CFG, helps identify these paths.
Control flow graph. That sounds related to cyclomatic complexity.
It is. Cyclomatic complexity, developed by Thomas McCabe, is a quantitative measure of a program's logical complexity. It's derived directly from its control flow graph. Essentially, it counts the number of independent paths through the code. A higher number generally means more complex logic, more potential for errors, and more test cases needed to achieve thorough coverage.
Okay. And briefly, what are the different levels of testing?
Testing usually happens in stages. Unit testing focuses on verifying individual components or modules of code, often done by the developers themselves as they write the code. It isolates parts.
And you put them together.
Right, that's integration testing. You combine individual modules that have already been unit tested and test them as a group, checking the interfaces, interactions between them. Following that is system testing, which is conducted on the complete integrated system as a whole. Its goal is to evaluate the system's compliance with the overall specified requirements, the SRS. It's often more about finding issues in the context of the full system.
And finally,
for custom-built software, there's usually acceptance testing. This is typically conducted by the end user or client to determine if the system satisfies their needs and requirements and is acceptable for deployment. It's the final check before going live.
and if any of these tests find errors, we get back to debugging.
Exactly. Debugging is that process of not just knowing an error exists, thanks to testing, but figuring out where it is, why it's happening, the root cause, and then fixing it. Common approaches include brute force, checking everything, backtracking, tracing back from the error, and cause elimination, hypothesizing causes and disproving them.
Moving on to Unit 8, software change management. You hear it all the time. Change is the only constant, especially in software. So managing change seems vital to avoid chaos.
Absolutely essential. If you don't control change, projects spiral out of control quickly. The core discipline here is software configuration management, SCM. SCM is all about controlling the evolution and integrity of all the software products and related items, source code, design documents, test plans, user manuals, everything that defines the software.
The key concept in SCM is the baseline. What is that exactly?
Think of a baseline as a snapshot, a formally reviewed and agreed upon version of a configuration item, like a specific version of the source code or an approved requirements document. Once an item is baselined, it becomes a stable reference point. Any subsequent changes must go through a formal control process. It marks a milestone.
What are the main activities involved in SCM?
There are generally 5 core activities. Configuration identification, giving unique names and versions to everything. Configuration, control the process of managing changes to baselined items. Review, ensuring changes maintain consistency and quality. Status accounting, recording and reporting what changes have been made, when, why, and by whom. And auditing and reporting, verifying that the process is being followed correctly and changes are implemented properly.
Version control is part of this.
Yes, version control is a key mechanism within SCM. It's the process and the tools used to manage multiple revisions of files, especially source code. It lets you track changes over time, revert to previous versions, and crucially, manage concurrent work by multiple developers without them accidentally overwriting each other's changes.
And the actual process for making a change, that's change control.
Precisely. Change control is the formal process for proposing, evaluating, approving, or rejecting, and implementing changes to baselined items. Typically, someone initiates a change request. This is then evaluated, often by a technical group or change control board, CTB, considering its impact, effort, risks, and benefits. This leads to a change control report.
Who makes the final call?
Usually, a designated change control authority makes the final decision accept or reject. If approved, an engineering change order, EKO, is generated, authorizing the change to be implemented. This formal process applies to baselines. Changes to things not yet baselined might be handled more informally. Auditing then confirms the change was made correctly.
All right, let's explore the modern landscape. Web, mobile, and case tools covering Units 9, 10, and 11. These introduce specific challenges and tools for today's applications, plus how computer-aided software engineering, CASE tools, help.
Indeed. For web software engineering, Unit 9, a key characteristic is often its layered architecture, typically client, application server, data layer. This offers flexibility. But development, testing, and deployment face unique challenges due to network variability, potentially massive user bases across diverse browsers and devices. User tolerance for slow or buggy web apps is notoriously low.
People just click away.
Exactly. So constant maintenance, performance monitoring, and content updates are critical. Key management issues involve handling evolving requirements, planning for scalability, configuration management across environments, and using relevant metrics.
What about mobile software engineering in Unit 10? What's distinct there?
In mobile dev, early visualization is key. Wireframes, simple screen sketches are used extensively to present and refine design ideas quickly. You also see prototyping mobile UI animations to ensure a smooth, intuitive user experience. Good wireframing clarifies the UI, flags usability issues early, engages clients, and saves costs down the line.
What are the crucial elements of mobile applications to consider?
Beyond just a good UI, you need a solid product strategy, great user experience UX, handling different screen resolutions, speed and performance, especially battery usage, user-friendly navigation, relevant content, security, offline functionality, maybe social sharing, and regular updates. The list is long.
And how are they actually built? Different approaches?
Yes, several approaches to development. There's native application development, using the platform's specific language, like Swift Objective-C for iOS, Java Kotlin for Android. This gives full access to device features and generally the best performance and security.
You have to build separately for each platform.
Right. The alternative is cross-platform application development. You write the code once, using frameworks like React Native or Flutter, and it runs on multiple platforms, iOS, Android. This offers uniformity, potential budget savings, and code reusability, but might have slight performance trade-offs or limitations in accessing all native features. There are also hybrid approaches, web tech in a native shell, and emerging things like rapid mobile application development, RMAD. and progressive web apps, PWAs.
And tying software engineering activities together, we have case tools in Unit 11. What exactly are they?
CASE tools stand for Computer-Aided Software Engineering Tools. They are essentially software applications designed to support and automate various activities throughout the software development lifecycle. Think of them as power tools for software engineers.
What are the main benefits?
They can significantly improve quality and productivity. They automate repetitive tasks, help enforce standards, improve documentation consistency, aid in analysis and design, like drawing DFDs or UML diagrams, support testing, and provide integrated project and configuration management. They help teams, especially distributed ones, collaborate more effectively. They support modeling, automatically generating code skeletons for models, and keeping models and code synchronized. Features like automatic version control and build management are often integrated.
Okay, let's wrap up this deep dive with some advanced topics. Process improvement and emerging trends, covering Units 12 through 16. Software engineering keeps evolving fast.
It really does. First, briefly, formal methods, Unit 12, use mathematical techniques for specifying and verifying systems. Because they're precise and unambiguous, they're often used in safety-critical or high-security domains where errors are unacceptable. Related is cleanroom software engineering, another rigorous methodology focusing on defect prevention through mathematical verification and statistical testing, rather than traditional debugging-heavy approaches.
We also hear a lot about software reuse and component-based software engineering, CBSE.
Yes, hugely important for efficiency. Software reuse is the systematic practice of using existing software artifacts, code, designs, documentation, test cases to build new systems. Component-based software engineering, CBSE, takes us a step further. It's an approach to building systems by composing them from pre-built, standardized, often independently deployable software components. Think of it like building with standardized Lego bricks instead of custom-making every single piece. The goal is faster development, higher quality, using proven components, and lower costs.
And process improvement frameworks.
Right, like SEI, CMMI capability, maturity, model integration, mentioned in Unit 13. This provides a framework for organizations to continuously improve their development processes, achieving higher levels of maturity and capability. Concepts like the first time right, FTR framework, incorporate best practices across the entire lifecycle.
Now let's hit some key emerging trends from Unit 14. What's big right now?
Well, low-code, no-code platforms are definitely gaining traction. These allow people, even those without deep programming skills, to build applications rapidly using visual interfaces, drag-and-drop components, and pre-built templates. They address developer shortages and accelerate time to market.
And AI.
Absolutely. Artificial intelligence, AI, and machine learning, ML, are pervasive. They're the driving force behind automation, enabling systems to learn from data and perform tasks that normally require human intelligence, natural language processing, image recognition, prediction, complex decision-making. Think chatbots, recommendation engines, intelligent automation. And underpinning much of this is the continued growth of cloud platforms, ILSS, SaaS, which are fundamentally changing how software is built, deployed, scaled, and managed.
Next, let's briefly touch on object-oriented design in UML from Unit 15.
Object-oriented OO design is a major paradigm. Key concepts you need to know include objects, representing real-world things, classes, blueprints for objects, encapsulation, bundling data and methods, hiding internal details, abstraction, showing essential features, hiding complexity, modularity, and inheritance, allowing classes to inherit properties from parent classes.
And UML is the language for this.
Yes, the Unified Modeling Language, UML, is the industry standard graphical language for visualizing, specifying, constructing, and documenting OO systems. Think of UML diagrams as the blueprints. They help everyone understand the system's architecture, components, and relationships. UML has different diagram types, broadly categorized into structural diagrams, showing static structure like class diagrams, component diagrams, deployment diagrams, and behavioral diagrams, showing dynamic behavior like use case diagrams, sequence diagrams, activity diagrams.
And finally, a look at data science for software engineers from Unit 16. How does this fit in?
Data science is becoming increasingly relevant for software engineers. It's an interdisciplinary field using statistics, machine learning, and domain expertise to extract knowledge and insights from data, often large data sets, big data. The typical life cycle involves requirement gathering, understanding the business problem, data preparation, cleaning, transforming data, data exploration, finding patterns, prediction modeling, using algorithms, and data visualization, communicating insights.
What are some common methods?
Key data science methods software engineers might encounter include clustering, grouping similar data points like customer segmentation, collaborative filtering similarity matching, used in recommendation systems, people who bought X also bought Y, regression methods predicting continuous values like forecasting sales, and classification methods predicting categories like spam detection using decision trees.
And that wraps up our pretty intensive deep dive into these critical software engineering concepts for your MCS-213 exam.
Yeah.
You covered a lot of ground.
We did. And as you continue preparing for your exam, remember that these concepts aren't just isolated definitions to memorize. They really build upon each other. They're interconnected, much like they are in real-world software development. Thinking about how these ideas fit together to build robust, high-quality software will not only help you ace your exam, but honestly, it lays a strong foundation for your future career. Good luck with your studies.